All right, thank you for coming. We have here today Dr. Cameron Tracy. He's a postdoctoral fellow in the Department of Geological Sciences in the Center for International Security and Cooperation at Stanford. He received his PhD in Materials Science and Engineering from the University of Michigan and his bachelor's degree from the University of California, Davis. His PhD was supported by the National Science Foundation Graduate Research Fellowship, and in 2015 he received a Young Scientist Award from the European Materials Research Society. His research focuses on the behavior of nuclear materials, including complex oxides and multi-component alloys in extreme temperature, pressure, and radiation environments. He previously worked as a research assistant at Los Alamos National Laboratory, and his colloquium today will be phase stability of nuclear materials in extreme environments. So let's welcome our speaker today.
Thank you for the introduction, and thank you for inviting me. I've had a lot of great discussions with the faculty so far today and the students as well, and I look forward to more. Before I start, I'd just like to make the point that at Stanford I'm in two departments, both geological sciences where I do scientific work, and also the Center for International Security and Cooperation where I do policy work, mainly focused on the disposal of excess weapons plutonium. I won't talk about that policy work at all in this talk in the interest of time and giving a complete picture of the science, but I do at the bottom give a citation here in case anyone is particularly interested in that, and I'd be glad to talk about it later on. But right now we'll be talking about the phase stability of complex materials in extreme environments. And now this is a two-part topic, obviously, complex materials and then the extreme environments they encounter in the fuel cycle. So first of all, sorry about that. Complex materials are found throughout the fuel cycle, and these include a lot of different types of materials. Of course, we have the nuclear fuel, which in advanced fuel cycles we might want to design such that it retains its properties, its integrity to higher burn-ups. We have alloys that form structural components in reactors. These have to operate ideally at even higher and higher temperatures to increase the efficiency with which reactors operate. They have to withstand radiation doses. And finally, we have, as another example, waste forms, which are meant to immobilize radionuclides for geological timescales. In the case of plutonium, which has a 24,000-year half-life, this includes many millennia. So just to give some examples of the complexity of materials we find throughout the fuel cycle, in the front end we have materials like uraninite, this mineral from which most of our uranium comes, which is a simple binary material in one sense, but also can have varying oxygen content, giving varying uranium oxidation states, so still chemically complex. We also have more complex ternary minerals, like here coffinite, granarite, uranium titanates, many different materials from which we extract uranium. Within reactors, we of course have the fuel, and I give an example here of how it can be more complex than just UO2. Here we add plutonium to it, giving us MOX fuel. We can also have a variety of different fission products in the spent fuel when we take it out of a reactor, so this is still a very compositionally and structurally complex material. We also have many advanced alloy concepts. These include things like oxide dispersion strengthened steels, high-entropy alloys that might be used in reactors to give better performance than conventional alloys. And finally, at the back end, we have a wide variety of very complex waste forms, which include compositionally complex crystalline materials, like this gadolinium zirconate pyrochlore I show here for immobilizing uranium. Borosilicate glasses are another example of a structurally complex material. And all of these highly complex materials have to, throughout the fuel cycle, operate and retain their properties in very extreme environments. Some examples of these environments include high temperatures from, of course, fission within a reactor, but even outside of a reactor, any actinide-bearing material is going to be subjected to decay heating. So that's important for the front and back end of the fuel cycle. You have the stresses or pressures that accompany fuel swelling, cracking in accident conditions, and also geological environments at the front and back end of the fuel cycle. You have crustal pressures associated with the burial of waste or ores that are located in the Earth's crust. And finally, what's really unique to the nuclear fuel cycle is irradiation. Any actinide-bearing material will be subjected to, for example, alpha particle or spontaneous fission fragment irradiation. And these two conditions are really interesting because they're what we call swift heavy ions due to the high energies or high velocities of these particles and their high mass. This, contrary to more conventional elastic collisions, knock-on collisions, causes electronic excitation, where electrons themselves in the irradiated materials are excited, which is a really extreme environment that can cause unique modifications. So these really can degrade materials, these combined extreme environments. So I show here what a UO2 fuel pellet might look like when you take it out of a reactor. It goes in as a pristine pellet. Due to these combined extreme environments, it comes out highly damaged, cracked, swelled, so on. So there's a lot of interest in simulating these extreme environments to see how materials might perform, to learn about how we can design better materials. So I show here 3 of those extreme environments and the techniques I use to access them in the laboratory. I subject materials to high temperature using resistive heating to get temperatures on the order of 1,000 Kelvin, which is about what you would find in a reactor. Diamond anvil cells are used to get pressures on the order of 1 megabar. In these cells, we squeeze materials between 2 ultra-hard diamonds to compress them to, if we want, pressures up to those found at the center of the Earth. And finally, we use heavy ion accelerators to simulate the effects of fission fragments or alpha particles by irradiating materials with these swift heavy ions, very high mass and high energy particles. Now, my experimental approach is based on simulating the extreme fuel cycle conditions of interest, which often involve these extreme conditions in tandem. So I use a sample encapsulation environment based around a diamond anvil cell. So we squeeze the sample here between 2 of these diamonds, which we can use to apply pressure, or if we're not interested in pressure, it's still useful because it seals the sample, which is nice when we're working with radiotoxic materials, especially when we're using them at user facilities like synchrotrons for characterization. We can heat the samples using heating coils through resistive heating. And what's nice about diamonds is that they're low density, so we can pass ions through them into our sample to simulate irradiation in a reactor or from alpha particle decay and so on. And also they're transparent. So for characterization, this is nice because most of my characterization I do at synchrotron facilities where I pass an X-ray through my sample, and then I can use the diffraction to learn about changes to the atomic structure in extreme environments. And I can put ion chambers behind and in front of the sample to measure the absorption of X-rays, which tells me about the electronic structure, changes to oxidation states of elements, and the chemistry, the chemical changes that are being undergone by this material. So I'll start by talking about some work I've done on fuel materials in extreme environments. And of course, for fuels, it's the dioxides that we're really interested in, particularly dioxides of the light actinides, things like thorium, uranium, plutonium, of course. These materials, as dioxides, are all isostructural. They all adopt this fluorite structure I show in the lower left corner. However, they have very different accessible oxidation states. So in this F block that I show at the top of the slide, below each element, I have the oxidation states that it commonly adopts in an oxide. And you can see that what's really unique among the light actinides from actinium to americium is that this changes dramatically as we move from one to the next. And this might be important for the radiation tolerance of these materials, because we know from studies on the light actinide analog material, cerium dioxide, that irradiation with swift heavy ions causes reduction of tetravalent cerium to the trivalent oxidation state. And that's interesting because among these light actinides, some of them, like plutonium, have accessible trivalent oxidation states, and others, like uranium, do not. So this might cause a dramatic difference in the radiation tolerance or the radiation response of these materials. So the question I asked here was, does this irradiation-induced chemical modification influence the radiation tolerance of these materials, their ability to maintain their structures and to maintain their properties under irradiation? To answer this, I compared mainly 2 materials, cerium dioxide and thorium dioxide. Now, these are nice model systems because they're very similar thermophysical properties, the same structure, this fluorite structure, nominally 1 F electron in the cations. However, they differ in one main respect. Thorium has only a tetravalent oxidation state. Cerium has an easily accessible trivalent oxidation state. So by studying these, we can really isolate any effects of this irradiation-induced redox behavior. So I first irradiated these materials with some different ion energies, different ion masses, and then characterized the structural changes using X-ray diffraction, which I show here, starting with the unirradiated sample at the bottom and an XRD pattern of increasing ion fluence as we move up. And you see there's actually very little change in the pattern. The fluoride structure is retained under irradiation, which is nice for nuclear fuels. Of course, you want them to retain their structures. But if we look very closely, we do see two small changes to the X-ray diffraction maxima. First is a shift of the peaks to higher D spacings, which is indicative of expansion of the unit cells, expansion of the structure, like they do to defect accumulation. Second, we see broadening of the peaks, which indicates heterogeneous microstrain, again, structural distortion, like they do to defects forming. We can quantify these two changes. On the top, the change in unit cell parameter, on the bottom, the microstrain as a function of ion fluence using Rietveld refinement. So I show here for the two different ions and energies, these changes as a function of ion fluence. And we see some really interesting behavior, particularly when we compare cerium and thorium dioxides. Thorium dioxide in blue shows a dramatic change in the extent of damage, the saturation damage for both properties, when we change the ion energy. Cerium does not. It's almost the same damage regardless of whether we're using 950 MeV gold or 167 MeV xenon. Now the behavior of thorium dioxide makes a lot of sense here due to the known effect of ion energy on the damage induced. So we know that the ion energy is proportional to the radial spread of excited electrons. So I show that schematically here in the lower right. When we have a low energy, low velocity ion, electrons don't travel very far from the ion path before relaxing, meaning that the deposited energy is localized. If we increase the ion velocity or ion energy, as shown on the right side, these electrons travel a long distance before relaxing, so the energy that we deposit is very spread out. What this means is that kind of counterintuitively, when we reduce the energy, we make more localized energy deposition, so we tend to end up with greater damage due to higher point defect concentrations induced. That's exactly what we see for thorium dioxide. When we move from 950 MeV to 167 MeV, the blue line, the damage induced, increases dramatically. For cerium, that does not occur. What we can conclude is that in thorium dioxide, due to the ion energy dependence we observe, we can attribute the damage observed to typical point defect production mechanisms of damage accumulation. In cerium dioxide, we do not see this expected ion energy dependence, so there's likely a different damage mechanism. The next thing we did is characterize the chemical changes that we know to occur using X-ray absorption spectroscopy. So I show here that measurement for both ion energies, and in both we observe a shift of the cerium K edge to lower energies following irradiation. That decreased electron binding energy is indicative of increased electron screening that accompanies the reduction of tetravalent cerium to trivalent cerium. So from these measurements, we know that on some cerium cations, additional electrons that have been excited are relaxing. Like structural damage, we don't see any dependence of this chemical change on the ion energy. Comparing the 167 MeV xenon and the 950 MeV gold, we see about a 2 eV shift in both cases. And we know, in fact, that the structural modifications we observe can be caused specifically and only by this redox effect, because trivalent cerium is about 20% larger than tetravalent cerium, so that can cause expansion of the unit cell, as we observed. We also know that if we're reducing only some of the cerium, we'll have a mismatch in the cation size between the trivalent and tetravalent cations, which will cause the heterogeneous microstrain that we've observed. So from this, what we can conclude is that in thorium dioxide, damage is due to a typical defect production mechanism, the displacement of atoms forming point defects. Whereas we have a very distinct cation valence reduction process that dominates the radiation response of cerium dioxide. So here, schematically, I summarize these two modes on the left and right. On the left, we show a typical or conventional defect production damage mechanism. On the right, the same structural distortion, similar damage from this redox mechanism. So from this, what we've learned is that there is an alternative damage mechanism, but one that is active only for some materials, those in which the cations can reduce from their tetravalent state to the trivalent state. This means, for example, that plutonium dioxide will likely have a very different radiation response than uranium and thorium dioxide, as in the latter two materials, you don't have reducible cations in the form where you do. And this tells us how by varying the composition of a fuel, we can to some extent tailor its radiation tolerance once we understand the mechanisms that are resulting in this damage. I talked about combining extreme environments, so of course an interesting thing now that we've induced radiation damage is to see how it anneals out, how high temperature modifies it. So what we did is annealed irradiated materials up to around 1,000 Kelvin, which is a temperature typical of what you would find at the center line of a fuel pellet. So I show here the change in unit cell parameter after irradiation as a function of annealing temperature. And again, comparing cerium dioxide and thorium dioxide, we see very different behavior. Thorium dioxide, as we might expect, has a single recovery step associated with the annihilation of point defects at relatively high temperature, about 800 Kelvin. Cerium dioxide has the same high temperature point defect annihilation step, but also at lower temperatures, a different low temperature recovery step, which is associated with reoxidation of reduced cerium. And we know that oxygen becomes mobile in cerium dioxide at about 500 Kelvin because it's often studied for use as a solid ionic conductor. And if we look at the derivative of the unit cell change as a function of temperature, we see that's really a good match. It's just a little bit before this mobility comes around and oxygen starts recovering that we start seeing this structural recovery. So what this teaches us is that there's a mechanism, once we understand the mode of damage, by which it can be mitigated. If we make oxygen mobile, this redox effect won't be so influential, won't reduce the radiation tolerance of this material. So next step we looked at was what happens if we irradiate this material at high temperature. So not annealing it later on, but irradiating it while it's at temperature like would happen in a reactor. And we see that if we increase the temperature at which we're irradiating this material from in red 300 Kelvin to in blue 600 Kelvin, so a fairly small increase in temperature, well below what is encountered, for example, at the center line of a fuel pellet, the swelling that is induced is nearly halved. And we know that at this relatively low temperature, 600 Kelvin, there's relatively minimal cation Fraenkel pair recovery. So it really has to be this oxygen mobility that we're inducing by depositing thermal energy to the material that mitigates this redox mechanism of structural damage accumulation. So what this shows is that by studying these atomic scale mechanisms of radiation damage, we can determine specific material properties or the composition and how that will mitigate damage, and determine conditions such as certain temperatures that might mitigate damage as well. The next thing we can look at is combining irradiation with high pressure. So what I did here is I took cerium dioxide, pressurized it to 20 gigapascals, and we see from the XRD data shown on the bottom that the fluoride structure is still maintained at this pressure. If we then irradiate this material while it's at pressure by injecting swift heavy ions into our diamond anvil cell, we see in the upper XRD a clear transformation to a new high density cottonite phase. So it's no longer the fluoride structure, it's now cottonite. And this is interesting because this is a typical high pressure phase of these dioxide materials, but it typically only forms at pressures far beyond that which we used in this experiment. For cerium dioxide, it's about 30 GPa, even higher for thorium and uranium dioxides. If we look at the transformation mechanism, we know that it involves the buckling of fluoride cation planes into adjacent anion planes. So we might conclude, therefore, that anion rearrangement, as we have seen in the last few slides, is induced by swift heavy ion irradiation, might have a strong influence on this transformation. In fact, DFT calculations show that the transition pressure varies a lot with oxygen content. So if we now know this irradiation-induced mechanism of oxygen sublattice modification, we understand that it will facilitate this transformation, extending the metastability range of this cottonite phase to even lower pressures than would be found in the absence of this coupled extreme environment. We've done the same experiments for uranium and thorium dioxide. We pressurize them to a pressure at which they maintain the fluoride structure, irradiate them while at that pressure, and for all three materials we see transformations to the same cottonite phase. So we've produced this material at pressures below that which has previously been produced using this extreme environment of swift heavy ion irradiation coupled with high pressure. The last thing that's interesting to look at in these actinide-bearing fuel-like materials are hexavalent uranium compounds. So I show again the actinide series with the oxidation states for each element, and you see that uranium is unique in that it has this hexavalent oxidation state, which is easily accessible. This allows it to form UO3 type phases, sometimes with water. I show here the gamma phase of UO3, which is the material I'll be focusing on here. These hexavalent uranium compounds are important for the fuel cycle because they're often products of reactor accidents where UO2 fuel is hydrated or oxidized, and they also form in geological conditions associated with the front end of the fuel cycle or the burial of spent fuel in a geological repository. Now these compounds have unique coordination, bipyramidal coordination of the very small hexavalent uranium cations. And what this results in are complex structures which are closely coupled to the specific hexavalent uranium coordination. And this results in strong coupling between the chemistry of these materials, the fact that they have hexavalent uranium, and their structures. It's such that we might imagine irradiation-induced reduction of the uranium would cause dramatic structural effects. So that's the question I was answering here. What happens if we reduce hexavalent uranium to lower oxidation states? Will these structures be dramatically modified due to the structure-chemistry coupling? If we irradiate these materials and characterize the chemistry using X-ray absorption spectroscopy, we see that following irradiation, we have the loss of this post-edge resonance feature, indicating the loss of hexavalent uranium and a transition to tetravalent uranium, as would be found in uranium dioxide. We then look at the structure, and as shown in this XRD data, there's a clear transformation from the initial gamma uranium trioxide structure in red to, in green at high ion fluence, a fluoride structure typical of UO2 or UO2 plus X. So here, this irradiation-induced redox behavior, which I've talked about, dramatically modifies the structure of this material, and we can predict that modification by understanding what happens to the chemistry of a material and how that chemistry is coupled to the structure. This allows us to predict how fuel cycle materials will behave in various extreme environments if we understand the mechanisms of degradation, of transformation. The next thing I'll talk about is specifically the back end of the fuel cycle, what happens to waste forms when we dispose of them in geological environments that entail extreme conditions. I'll talk mainly about complex ceramic waste forms, which are a likely candidate for use in this application, but which have to meet a lot of very stringent requirements. The first of these is that we want a material that can incorporate many large cations in solid solution, because the waste streams out of a reactor are very complicated. We need to put in things like actinides, uranium, of course, but plutonium and minor actinides as well. We'll need to incorporate fission products like lanthanide, cesium, so on. We also want a material that won't leach in groundwater, because the whole idea here is to immobilize these radiotoxic materials to prevent them from reaching the biosphere. So if they leach into groundwater, that's of course dangerous. Finally, because these materials remain radiotoxic for geological timescales, tens of thousands of years or longer, we want these materials, these ceramic waste forms, to be very highly stable under sulfur radiation, because they will be self-irradiated for millennia. So the question here is how these disposal environments that include decay heating, sulfur radiation, crustal pressures, will influence the structure of these materials and therefore their critical properties to perform as a waste form. And the approach here is, because these are very complex materials with complex compositions, therefore complex structures, is to characterize the specific disordering mechanisms they undergo at the atomic scale in these extreme environments. So I'll be focusing mainly here on one waste form type, the pyrochlore materials, which are A2B2O7 materials. And these are nice as waste forms because they can incorporate a lot of different cations. On the A site, you can fit large tri, di, or monovalent cations. So these include things like lanthanides and actinides. Whereas on the B site, you can fit smaller tetravalent or pentavalent cations, so things like transition metal fission products. They also have exceptional chemical and structural flexibility, so we can fit everything in quite nicely into a pyrochlore structure, which is based on the fluoride structure, so it incorporates things like actinides very well. Finally, they have high actinide retention due to strong bonding and coordination of the actinides. And they can often maintain their crystallinity and therefore their properties during self-irradiation, because they have access to a unique pyrochlore to fluoride disordering mechanism that allows the pyrochlore superstructure to disorder to a fluoride-like structure while still maintaining its crystallinity without becoming amorphous. So that disordering mechanism involves the mixing of the A and B site cations onto a single crystallographic site, as well as mixing of oxygen and vacancies onto a single crystallographic site, such that this pyrochlore structure becomes a disordered yet crystalline fluoride structure. And this is, as I mentioned, important for waste form performance, because crystalline materials tend to retain actinides to immobilize them better than amorphous materials, because in crystalline materials we maintain the local bonding of a radionuclide, such that it is held in place, it's less susceptible to leaching by groundwater, for example. So this disordering mechanism allows the energy deposited by radiation, by decay heating, by pressure to be dissipated without losing the crystallinity of the material, so that we can expect it to retain its nice immobilization properties. So I show here XRD data for what happens when we irradiate one of these radiation-tolerant pyrochlores, and you see that as we move from bottom to top, these intense peaks corresponding to the fluoride substructure are retained, and we only lose these very weak peaks corresponding to the pyrochlore superstructure. But yet, even at very high ion fluences, as shown in orange, the material remains crystalline. It still has clear XRD diffraction maxima. Now, there is a strong compositional trend in this radiation tolerance. If we substitute the A site cation in pyrochlores with a large lanthanide, then you see at high ion fluence, we have these broad diffuse XRD scattering maxima, which are indicative of an amorphous material. So some pyrochlores do amorphize under irradiation. However, if we substitute smaller lanthanides, such as ytterbium, onto the A site, they will retain their crystallinity by accessing this pyrochlore to fluoride disordering mechanism. So I show here TEM micrographs of ion tracks in these different materials, the results of irradiation with a single ion. And you see for materials like neodymium stannate on the left, we have these large amorphous regions that are induced by irradiation. Under the same irradiation conditions on the right, ytterbium stannate shows very little damage, just some contrast, probably due to a few point defects in there. Implications of this compositional trend mean that we now have a material property from which we can determine the resistance of this material to amorphization. That is the cation radius mismatch, or Ra over Rb, because we see that, as in this plot here, the fraction of material that is amorphous as a function of ion fluence decreases when you decrease this Ra-Rb ratio. So that's nice. A typical conclusion would be that we can now design better waste forms by making materials with low Ra-Rb ratios such that they maintain crystallinity when we irradiate them, because we know that in this case the bonding will be maintained in the absence of amorphization, so immobilization will still be effective. However, there's a big shortcoming to this. So far, I've shown XRD data, and this is what most of us work on, as well as TM data, which is still characterizing the symmetry of a material, the long-range structure. Bonding is a short-range local structure property. Previously, this hasn't been characterized very well, but that's what we should really care about if we're thinking about the immobilization of radionuclides. So what I did is characterize the local structure of these pyrochlore materials before and after irradiation, first using Raman spectroscopy. Now, in this technique, we get peaks that correspond to phonon vibrations, so vibration of bond pairs, which really tells us about the local bonding and immobilization properties of these pyrochlores. So I show here for neodymium stannate what this looks like, how the Raman spectra evolved as a function of irradiation. And you see the initial spectrum is clearly changed. New peaks arise. Those peaks we have initially are attenuated. But if we compare the high ion fluence, so the heavily damaged Raman spectra, of a lot of different pyrochlores, remembering that some of them, like neodymium stannate, according to XRD, are amorphous, whereas others, like ytterbium stannate, according to XRD, is still crystalline, just in this disordered fluoride structure, we have some interesting observations here. First of all, they all have very complex spectra, none of which are consistent with a fluoride local structure, which only has a single Raman mode. Second, we have almost the same spectra regardless of whether, according to XRD, these materials are amorphous or whether they're simply crystalline yet disordered fluorides. If we compare the Raman spectra of all of these irradiated pyrochlores, which I mentioned are very similar, to those from the literature for Weberite structured crystalline compounds, we see that they match very well. These Weberite compounds are typically A3B07 stoichiometry, so we can think of them as stoichiometrically defective pyrochlores. But they have cation bonding environments that are almost identical to the pyrochlores. So if this research tells us that the disordered or amorphous pyrochlores all locally have Weberite type structures, they will all, regardless of their long-range structures, have almost the same local bonding environments. We've confirmed these results using neutron total scattering, so I show here a pair distribution function resulting from those measurements, where peaks correspond to local atomic pair spacing. So again, this tells us the local coordination structure. And here I show blue circles, which are experimental data from a disordered pyrochlore, and then a red line showing a simulated PDF for a Weberite structure model, and we see the match is great. The green difference curve at the bottom is very small. So this confirms that a Weberite local structure is formed in all of these pyrochlores when we disorder them or amorphize them. And in fact, this same local structure is formed regardless of what extreme environment it is that is damaging these materials, if it's irradiation, if it's pressure, if it's high temperature. So what we've learned from all of this is that the local cation bonding and therefore the radionuclide immobilization properties of these waste form materials are maintained whether or not they lose their long-range structure under irradiation. So counter to what we thought for a long time, amorphization doesn't seem to really matter for this specific property for the leaching of these materials. This is a way that the study of waveform behavior in extreme environments can elucidate atomic scale mechanisms which allow certain materials to withstand damage, to maintain their properties despite structural damage from these extreme environments in which they operate. And this is useful for the design of better materials. We obviously don't want to simply design materials with ideal ionic radius ratios, because that doesn't really matter. What matters is the immobilization properties. And so we want to design materials that have access to this local Weberite structure disordering mechanism. Finally, I've shown a lot of instances in which simulating extreme environments tells us how a material will perform in the fuel cycle. But what's really interesting is that these phase transformations, these disordering mechanisms we induce, can be useful as a processing tool to make new materials that might perform better in the fuel cycle. So the idea here is to use these extreme environments to synthesize new, possibly useful phases. And this is important because many advanced fuel cycle concepts are hindered by the inability of materials to withstand these extreme environments for long time scales, to withstand high temperatures, to withstand high burn-ups and irradiation doses. By conventional processing, we're limited in the new phases we can make. We might heat a material, we might mill it, but there's only so much that we can make, so many different phases we have access to. The recent accessibility of extreme environments at the laboratory scale might give us access to a range of new phases that might have interesting or useful properties or might be more resilient in extreme environments. So that's a new research direction, to harness these extreme conditions, not just to explore how a material will behave, but to try to make new materials that might behave better. So the first research I'll talk about here is on the lanthanide sesquioxide system, which is nice for a few reasons. First of all, its high temperature polymorphism, which I show here, shows that it's a nice analog for the actinide sesquioxides, especially if we look at the same ionic radius range in both materials. So we see similar A, B, C type polymorphism in these materials. Polymorphism is also something we like in this system because we have access to a lot of different phases. So if we're interested in using extreme environments to get specific phase transformations, to access the phases that we might not be able to in the absence of extreme environment processing, this is a great model system to look at. We're particularly interested in two phases, the H and X type, because these are non-recoverable, or were previously non-recoverable to ambient conditions. They form only at very high temperatures or very high pressures, and have never been before recovered to ambient conditions at which they might be useful in an engineering application. They also have very unusual structures because they only form in these extreme environments, and unusual structures typically give rise to interesting and maybe useful properties. So we irradiated a number of different lanthanide sesquioxides, those highlighted here, and saw some phase transformations. And those highlighted in orange, the three lightest lanthanides, they're sesquioxides, as shown by the XRD data here, transformed from initial C-type structures to B-type polymorphs. Now this isn't so interesting. The B-type phase we can make through conventional processing means. However, when we irradiated sesquioxides of the two heavier lanthanides, we saw a transformation to this X-type phase that I mentioned, as shown in the XRD data here. Now this is really interesting because we're stabilizing this X-type phase not only for the first time to ambient pressure by making it through irradiation, such that it is metastable after irradiation, but we're also extending its metastability range in composition space. You see from this phase space diagram that it forms only up to holmium sesquioxide. However, we've formed it for thulium and lutetium sesquioxides, so we've extended not only the temperature range of metastability, but the composition space. And this shows us how extreme environment processing allows us to access new kinetic pathways and stabilize new phases. Now, the fact that we stabilize this phase is really interesting because when we tailor the irradiation conditions, we can make, for some materials, such as lutetium sesquioxide, a pure X-type material, which, again, hasn't been made before. We can now characterize the structure of this material, which wasn't well understood previously. We know that it has a body-centered cubic cation sublattice, but the anion sublattice was previously unknown because it could only be formed at very high temperatures. It couldn't be easily characterized. We performed neutron scattering experiments to determine the positions of oxygen in the unit cell of this material. Now, from the known cation structure, which we know from XRD, there are two possible sites for oxygen, one octahedral site and one tetrahedral site. So I show those two structures here on the right, on the top the tetrahedral and on the bottom the octahedral. Using neutron diffraction, we can really see the position of oxygen because neutrons scatter strongly from oxygen, unlike X-rays. Also, because we've stabilized this material to ambient conditions, we can perform this diffraction at low temperatures, such that there's minimal thermal displacement. We get relatively nice signal. So I show in red the neutron diffraction pattern from an unirradiated material, and in blue the neutron diffraction pattern from an irradiated material, as indicated by these horizontal dashed gray lines. There are new peaks that emerge after irradiation corresponding to this X-type structure. We can compare the intensities of those peaks to these black lines on top, which are the simulated diffraction patterns of these two potential structures. And we see that the match of the experimental data is great for the structure with oxygen in the tetrahedral site and poor for that of oxygen in the octahedral site. So we've solved the structure of this material now. And we see, really interestingly, that in this structure, oxygen occupies one of 4 sites on each cell face, giving it a 25% site occupancy, meaning it's very highly disordered. This is unusual and interesting, particularly if we compare it to another material, alpha phase silver iodide. Now, this is the material that ionic conductivity of a solid at relatively low temperatures was first observed in. It's the prototypical ionic conductor. It has a body-centered cubic arrangement of iodide, with silver preferring to occupy low occupancy sites, tetrahedral sites on each cell face, making it nearly isostructural with lutetium sesquioxide. And in fact, the exceptional ionic conductivity of silver iodide emerges from its unique structure. It has a rigid sublattice to provide mechanical stability coupled to a liquid-like sublattice where ions can travel freely through the free volume not occupied by the rigid sublattice. So its ionic conductivity emerges from this unique disordered structure, which is nearly the same as that of lutetium sesquioxide. So in this case, dense electronic excitation has, for the first time, produced a new phase of lutetium sesquioxide stable at ambient conditions such that it can be used in applications, which has a unique structure that is highly favorable for oxygen ion conduction. Another system I've looked at are metals, high-entropy alloys, which are near equiatomic solid solutions of 5 or more metal components. So these are a recently discovered class of material, or I should say recently used in engineering applications. They were first discovered in nuclear fuels as epsilon particles, but only within the last decade or so has it been recognized that they have really unique properties. So I show here in the lower right the specific strength of different materials, and you see that the high entropy alloys in this orange blob have specific strengths superior to that of virtually all conventional metals and alloys in this red blob. So they have nice properties that are in many cases attractive for reactor applications. However, by conventional processing, we can access only, or typically we can access only 2 phases in these materials, body-centered cubic and face-centered cubic structures. That's true of most transition metal high entropy alloys, which are those that might be used in reactors. And this is despite many attempts to make hexagonal close-packed high-entropy alloys, which have failed. However, their processing by extreme conditions has not been pursued previously. So there's an opportunity here to look at, for example, the high-pressure phase space of these materials and see if we can make this unique HCP phase. In fact, when we pressurize this material, as shown in the XRD data here, starting with the ambient pressure XRD pattern and pressure increasing as we move up, we see a clear phase transformation of the prototypical high-entropy alloy chromium, manganese, iron, cobalt, nickel from the initial face-centered cubic structure to a hexagonal close-packed structure. This is what a lot of people have been trying to do. We've now done this. It's useful because HCP materials have relatively few slip planes compared to FCC, making them typically quite hard. So hard materials are sometimes good, ductile materials are sometimes good. Regardless of what we want, we need to, again, quench this material to ambient conditions. So when we reduce the pressure, we quite surprisingly see that much of this HCP phase is retained. I show here on the upper right XRD data for materials quenched from 54 GPa and 25 GPa, and we see that there is quite a lot of signal from an HCP phase, even after we've removed the pressure. And as I show on the bottom, the HCP fraction, which you end up with, is proportional to the pressure you achieve when you pressurize the material, meaning that we can tailor mixtures of the hard HCP and ductile FCC phases, meaning that we can tailor the mechanical properties of these alloys. So here again, extreme environment processing yields for the first time a new phase, and it also allows us to tailor an interesting property, the hardness of these materials in this case. Now, a lot of the research I've talked about in this area so far is really exploratory. We pick an interesting material and see what it does, and in a lot of cases it makes something quite interesting when we expose it to extreme environments. However, there's opportunity here for more targeted development of, for example, fuel materials. So I want to go back to two topics I've talked about. First, on the left, when we irradiated lutetium sesquil oxide, we saw that the irradiation-induced electronic excitation yielded extremely high anion mobility, this ionic conductivity in this material. In research I talked about before, when we irradiated cerium dioxide, we saw that anion mobility, or the mobility of oxygen atoms, can mitigate a mode of radiation damage, yielding high radiation tolerance. So we might envision a situation in which electronic excitation or extreme environment processing causes anion mobility, and this anion mobility yields exceptional radiation tolerance that might be superior to that of materials we can access through conventional processing. This is especially interesting because a possible nuclear fuel material, uranium carbide, is isostructural with lutetium sesquil oxide. So we might ask, does it undergo this same transformation to this unique X-type phase if we process it with these extreme processing conditions? And if that does happen, does the anion mobility associated with this phase yield better radiation tolerance? So to summarize, we really need to understand the solid state chemistry of materials throughout the fuel cycle, particularly that solid state chemistry that occurs in extreme environments. Because we need better fuels, we need waste forms that can immobilize radionuclides, we need metals that perform at high temperatures, and so on. By studying materials in extreme environments, first of all, we can understand the fundamental atomic scale physical mechanisms that control degradation, such as this redox effect, the disordering I talked about in pyrochlores, allowing us to come up with ways to mitigate them. However, we can also in some cases synthesize new materials with interesting properties. So there's a real opportunity here, based on the previous results I've discussed, to produce materials using extreme condition processing that are then exceptionally tolerant or resilient in other extreme environments, which is exactly what we need for advanced fuel cycles. So thanks for your attention, and I'd like to quickly acknowledge collaborators, particularly those at international institutions in Russia and Germany, where we do our irradiations, as well as those in national labs that provide us with high-entropy alloy samples and characterization using these synchrotron X-ray techniques. Thanks.
Do we have questions for us? No? Okay, Ed?
Looking at your slides, it looks like your record number of components is 6.
In the high-entropy alloys.
Yeah, we're just in the whole talk. And my point is, when you have fission products, you have a dog's breakfast of things going from Z equals 1 to 97 or something. Has anyone ever made a surrogate of spent fuel that would have the isotopic mixture that it would have 1 year out and 100 years out and 10,000 years out?
Yes.
And then look at the mechanical and do the same with that material and try to discern what's really going on in there.
Yeah, there actually has been a lot of work into making low radioactivity simulated spent fuel. The issue is that a lot of the time the specific way in which these components are incorporated isn't really well understood. So we can say it's in solid solution, but is there clustering, things like that. So there has been a lot of work in that area, but it's always a little bit questionable how accurate it really is, how well it does reflect what spent fuel looks like in terms of local atomic structure and things like this.
Yeah, it's just that if you had spent nuclear fuel, it's not likely that you could say, okay, put the technetium over here and the moly over here and all that kind of stuff. So.
Don?
You showed a number of microscopic effects of these various phenomena on these materials. What would the macroscopic effect? I mean, what would you have to worry about if it were a waste form or a fuel element in the real situation, not in a spectroscopy sense?
Yeah, so a lot of the properties change really dramatically. So for example, in a waste form, if we amorphize it by irradiation, even though the local structure might not change a lot, the density changes. So sometimes if you have a monolithic pellet, for example, if there are density changes, it might break apart into a powder, things like this. With nuclear fuels, there are really clear mechanical changes. So even though we're just introducing point defects, this really changes the bulk modulus of the material, the hardness. Oftentimes it becomes more brittle. because you have a lot of defects in this material preventing collective atomic motions. So there are very clear property changes and often very clear changes in the bulk, even shape of your material. It might fall apart, it might no longer be mechanically
Well,
stable.
what sort of point defect concentrations do you need to actually get a visible macroscopic effect, say crumbling of the material?
So it depends a lot on the specific material. Things like uranium dioxide, where you typically don't see gross changes at relatively low ion fluences. So typical of maybe the first 10 days of reactor operation, if we agree with the extent to which we're simulating that, then we can see clearly measurable changes in the mechanical properties, especially hardness. That happens rapidly.
Now, these effects would anneal out at high temperature. Now, I don't know what temperatures you are normally using for these tests, but reactor temperatures can go up to, at fuel center line, 2,000 degrees Kelvin.
Yeah, so we did some simulation of this annealing effect by taking our irradiated material and then putting it in the furnace and seeing what happens, at what point the damage disappears. And we see that in a lot of cases, a lot of the damage is annealed out at temperatures that are fairly low in terms of the center line of a fuel pellet, 800 Kelvin or so. But in the rim of the fuel pellet, where a lot of interesting stuff is going on, like rim effect restructuring, temperatures are significantly lower. And at temperatures below about 800 Kelvin, we can have quite a bit of damage that isn't recovered. So even at fairly low temperatures, or temperatures that would be encountered in a reactor, so excuse me, fairly high temperatures, some of this damage is retained. And we know that everything isn't annealing out, because if we characterize the structure of spent fuel and fuel before we put it in the reactor, we see that the defect concentrations are, at least at the rim, clearly different. So yeah, a lot of it will be annealed out, but some of it won't be.
Have you ever actually looked at these specimens after they've been, just from a macroscopic point of view, after they've been exposed to these environments? What do they look like? Have their original shape, original hardness, or are they really vastly changed so that you worry about them in a practical application?
Yeah, so I don't have an image of it here, unfortunately, but you can, just by looking at if we make a fairly thick pellet and then irradiate it, the expansion is to such an extent that if you look closely, you can see it's a different size. If you look at it with a optical microscope, you can often see porosity that's induced by irradiation through the aggregation of defects. So there are some really clear visual changes at high enough ion fluences, but still those that are typical of not exceptionally high burn-ups. Another thing that changes that's interesting is the color, and that's something I've been looking at lately because this is somehow related to the oxidation state of our cations, most likely. So that's something that I don't think anyone has really characterized, but often we'll put in a material like thorium dioxide where it's a frank white, and when we take it out, it's dark green or something like this. So I don't know exactly what that means, but that's more evidence of really dramatic changes going on in the crystal chemistry of these materials.
I have a couple of questions, follow-up from Don's questions, really. So you did the ion beam irradiation at room temperature?
So we did it at room temperature. We've also done it at higher temperatures, as I show here, and measured how that affects the behavior.
Okay. So that's the irradiation temperature, 600 Kelvin.
Yeah, we've done 300 Kelvin, 600. We did higher, 900, 1200. So there's show similar results here.
So that post-irradiation annealing treatment wouldn't necessarily be the same as high temperature during irradiation because
Yeah.
the kinetics matter, right?
Mm-hmm, exactly. So that's why we've done both.
Right. But so in the fuel, as Don pointed out correctly, of course, there's a much higher temperature than 600 Kelvin.
Mm-hmm.
So, well, your annealing goes to higher temperature as well. Would you expect that some of the effects go away at higher temperature irradiations?
Yeah, so I don't have the data here, unfortunately. I wanted just a simple diagram, but we do see a monotonic decrease in the damage induced as we increase the temperature. But we did experiments at 900 Kelvin and 1200 Kelvin, and in both of those, there is still measurable expansion of the unit cell and measurable microstrain.
Can you then say something about the kinetics of the annealing treatment, or the kinetics taking place in that? Because for metals, it's happened so quickly that you would have to go the opposite way, you have to go to cooling, right? But you have the benefit of being in ceramics where you can go higher up and actually can test those. So can you say something about the kinetics and therefore maybe of a long-term stability for waste forms?
Yeah, so kinetics are kind of tough. We can say a lot about the energetics based on what changes with temperature. The kinetics, unfortunately, we typically don't do online in situ characterization because we do these irradiations at large ion accelerator facilities. We have to ship them there, or bring them there, and do the irradiation. Usually we use mini samples, which we irradiate to many different fluences. So each of these data points is a separate sample that has been irradiated only to that fluence and then later characterized. So we can't get a lot of kinetic information just from that, but it is possible. And this is why what we're working on right now is the use of femtosecond lasers to simulate the effects of Swift-heavy ions, because this damages materials again by electronic excitation, but it allows us to do pump probe type experiments where we can really see in real time what's going on.
And also following up on this pyrochlore to fluoride structure transformation. So it maintains crystallinity,
Yeah.
but it changes phase, so potentially it can still tear itself apart and crumble to dust, right?
Yeah, although in here, this is why I use the word disordering. It is changing phase, but we can also just think about it as a high concentration of two defect types. If we mix the A and B sites, then it's just an anti-site defect. So it's not really a different phase. And then if we mix oxygens and vacancies together, it's just kind of just like a high concentration of anti-Frankel defects. So it's in a way the same structure, just highly defective rather than a complete phase transformation.
So following up on Don's question, did you observe cracks?
No, we've never seen cracking in a pyrochlore. We do see changes in mechanical properties, as with the dioxides in these. They become much harder after we irradiate them.
And Y2TI207 is one of the pyrochlores which we find in ODS alloys, as you mentioned ODS alloys earlier. Where would that fall on the radiation tolerance?
So if we base it on the ionic radius, yttrium is right around erbium. So it's fairly tolerant. And a lot of people have been studying under alpha particles, like Bob Odette at UC Santa Cruz, what happens there. And they are, as we expect, fairly tolerant. They usually maintain crystallinity and don't amorphize, which is nice for steel because these interfaces, of course, matter a lot.
Yeah, they also did like neutrons, 120 dPa neutrons, so it's maintained it. So.
Yeah, so that's another application of pyrochlores, not only as waste forms, but also as components of these advanced alloys for which this disordering mechanism is, again, pretty important.
Any other questions?
One more, Robert. What sort of burn-ups in terms of the fluence did you go to in these?
So it's hard to give a one-to-one correspondence simply because the fission fragment rate changes depending on where you are in the fuel pellet. And as well as things like the time scales involved. If we're talking about high temperatures, it depends on the flux we're using. So it's really tough to say what is the burn-up equivalent. So instead, what we usually think about it in terms of is just saturation, because of a certain ion fluence under specific conditions, damage tends to just saturate and not change after that point. So usually we just try and get to saturation and say that at a very high burn-up, this is what will happen, rather than saying, I don't know that it's possible to really accurately say this data point corresponds to this burn-up. But that would be nice. I mean, that would be a goal, and if we can get to that point by characterizing really at the atomic scale what's happening during fission fragment irradiation and our Swift-heavy ion irradiation, that would be very nice.
Well, you can kind of say like 10 to the 14 is kind of like 65,000 megawatt days per kilogram.
Yeah, we can get some rough estimates.
Yeah.
Does the saturation just say you've reached kind of some maximum disorder that you just can't go beyond?
Yeah, so
kind of
typically
homogeneous?
what's happening is that you're just depositing a lot of energy to the electronic subsystem of the material. So as everything relaxes, it's going to have some final damage state. If you hit a damaged region with another ion, it's going to go through the same process where everything is damaged and then some of it recovers to the same end state. So what's really happening here is the change in coverage of our sample, where at a certain, say, intermediate ion fluence, not all of the sample has yet been hit by an ion and yet been damaged. So it's not really an accumulation of more and more defects in the same area, it's just more area being damaged in our samples.
So there's no more questions.
One
Max,
more.
sorry. Okay.
You talked about using these kind of processes maybe to create new materials or different properties. So I'm assuming that right now you're working with small components. So when you go from small components to actually building things, you have to go through the manufacturing process. Do you think you'll be able to retain these properties, or have you thought about what would be the step from components to bulk materials?
Yeah, that's a good question. That's one of the things I'm working on a lot right now. For example, through the electronic excitation from swift heavy ion irradiation. That's probably not so feasible to do on an industrial scale. What is more likely is to use something like a femtosecond laser that can be done on a much smaller scale, much more cheaply. And so that's why I'm studying what happens when we irradiate large areas with a femtosecond laser. Do we get the same transformations? Do we get similar transformation rates and so on? Another example, high pressure, which we used on this high-entropy alloy to make the HCP phase. Diamond anvil cells involve very small samples, diameters on the order of maybe 50 to 100 microns. But we also have large volume presses that can make samples large enough for testing in a tensile test frame. So that's something we're studying to see at these larger length scales. Is there any change in the phase transformation induced? And if there isn't, that's great, because then we can really characterize these mechanical properties in a typical engineering fashion.
Don had another question? No.
Yeah, one more. You have that fact in this slide, there's a factor of 2 difference in the swelling. When you go for a relatively small, low fluence and change the temperature by 300 Kelvin, well, at those temperatures, even 600 Kelvin in UO2, the oxygen mobility is vanishingly small. If you say you take UO2 plus X and measure the oxygen diffusivity in that, it's nowhere near what you get, what you're implying from 600 degrees Kelvin.
So a lot of this, I kind of rely on literature from the ionic conductivity community. And for cerium dioxide, I don't know exactly off the top of my head what the numbers are, but they talk about a strong cutoff between immobile oxygen and some sort of measurable, appreciable oxygen mobility at about 500 Kelvin. So I'm not sure what the numbers are, but at least from that literature, that's how they discuss it and what I've relied on. I'm not sure yet. Maybe it is much lower than at higher temperatures, and that might temper this explanation to some extent.
Uranium dioxide.
Mm-hmm. Do you know if the other actinide dioxides are similar, thorium and cerium?
I would think thorium is even more difficult to move the oxygen around than uranium dioxide.
Mm-hmm. Yeah, so that's interesting. Maybe there is some significant influence of electronic excitation on the mobility of the oxygen than if we know it is moving around, because we do see this redox effect. So maybe it's not just the temperature, it's the fact that that's coupled with the radiation. That's an interesting thing.
Well, it's also the radiation damage. What fraction of neighboring sites are vacant?
Yeah, and if we're knocking oxygen around, it will definitely
That's right.
change it.
If there's more questions, then thank you.